Hello everyone. Since we are not in the classroom, I'm gonna deliver the last lecture in the clutch and brake system, and I'm gonna summarize a little bit about the final exam at the end of this video. So I guess if you follow the online lecture, I believe that you left over from the clutch design. Let me see if I can find the clutch design. Yes, so again, I attached the lecture note on Blackboard. So if you follow up, the last problem we worked on was the evaluation of the total inertia and then time for a given torque T. This is G unit system where you have multiple gears, and so we actually tried to evaluate all the inertia with the given gear ratio, and then we calculated the inertia term, WK square, and then find out the time, T. So what we will continue on today is to discuss a little bit about the energy absorption. The energy, here we are talking about kinetic energy, KE, which is evaluated by the equation of 1/2 inertia I times rotational speed W, omega per second square. And then the I, the inertia term, is going to be usually evaluated by the mass times K square, which is the radius of gyration. And then it's going to be eventually this equation right here, M, K, W, and 2, and then you divide it by G if you use weight, so that the unit should be Newton times meter. And if you change it to the US customary, you just have to divide this by 32.2, and then you can change it to the RPM by using this unit right here, revolution per minute, to give us this equation of the energy absorption in US customary. So if you know RPM and if you know the inertia, you can find the energy absorption by this equation. And this number 4 here. So one problem here, we're gonna talk about we're gonna solve one problem for energy absorption later, but let's solve one in your textbook 22-5. And this problem is asking for the total cycle time and then the energy absorption. So it has the clutch and brake system, and then if you collect all the given data, you have a torque T, 240 pound-feet. Again, this is the same system we solved in the example, let me see, 22-3. So the time, the entire time layout is given right here in your textbook. So if you follow this up, first thing you have to do is to find some basic information about the response time, and those response time is coming from your textbook. Let me see if I can show this to you. So if you look at the table 20-2, depending, not this one here, sorry. Yes, this one here, clutch brake system. Depending on the torque and then the inertia, you can predict the response time of the clutch and brake, and then heat dissipation. So, I mean, you can calculate this, but this table makes everything easy. So you can figure out these response time quick. So basically, for a given 240, the response time here for the clutch is 0.235, same as the brake, 0.235 second. So with this response time, you can actually start with the clutch. This is a clutch. Let's see. Response time. This is basically the time that you apply the clutch. So it takes about 0.235 from the table response time, and then once clutch is engaged, and you actually accelerate along this profile for about 0.088, and this number is came from the exercise 22-3 to reach up to 550 RPM. So once you get into this, the cycle says you need to let it on for 1.5 second, and then off. I mean, not off, but you apply the brake after on time. You apply the brake right here, and then brake response time is again the same as the clutch response time, which is 0.235. And then because of you decelerate, it's going to be decelerating at the same rate as the acceleration. So we have to apply the same time of 0.088, and then after this second, the whole system will be off for 0.75 second, 0.75. So if you add all this up, the total cycle time of this system is 2.896. And then the energy absorption is again from this equation, and you actually figure out the W and then K from the problem 22-3 we found, and it gives us the value of 608 pound-feet. That's the energy absorbed by this brake system. So that wraps up the clutch, and then we can actually move on to the drum. The brake. There are two brake systems we will talk about in this lecture. The first one is a drum. The other one, I think, is that bend. So bend is right here. Bend has a little bit different shape, but the drum brake is the most classical drum system, the brake system, where you apply the force with a lever, so that this force will be amplified by the leverage effect to cause the friction right here. And then this friction actually again is a function of the normal force. The normal force is a function of the force that you apply. So if you want to calculate the W that you need to apply to stop this, assuming that everything is in static equilibrium, we take moment at the point of A0, which is the rotational center of the lever system, and assuming here WL, we're going to just apply this direction positive, so that the W here times L is going to be positive moment with respect to the center of rotation at point A, and then N, assuming that the N is applying at the center of this contact point, N times A, which is the distance from the center of A to the contact, the force N, is negative because it is causing clockwise moment. And then another force that you need to consider is friction right here, because it is off from the center A by B. So FF times B is going to cause the what is it? I think it should be negative. I don't know what is the positive. Sorry, negative moment. But this basically depending on the direction. If drum was rotating this way, rotating this way, the FB should be going that way. If it's going that way, this is positive, yes. And then because again the friction is the friction coefficient F times the normal force N right here, we can calculate the W, which is the force you need to apply, as a function of friction force, and then the geometry of the lever system A, B, and L, and then F, which is the friction coefficient. Okay. So with this in mind, you can actually calculate friction F as a function of W that you applied. And this, if I know the friction F, and then if I know the dimension of the drum, then I can calculate the torque that I can handle. So that's how you calculate the friction torque. So with that in mind, there is a problem that asks us to solve for the W for a drum brake for a given torque Tf. So simply, if you collect all these dimension of the drum, and then the lever geometry, friction coefficient, and then this is again B. This is from the center of rotation to the friction. You can calculate F of F, which is friction force that's going to occur at the contact point between the drum and then the friction pad, which will be simply Tf over R, because the diameter is given. You need to just divide it by 2. So that gives us 120 pound. And then W, which is coming from the previous equation W, the actual force you need to apply, is going to be calculated by the F of F, and then A, B, L, all given geometry, and then the friction F. So if, as you change your friction for given data points right here, you can actually calculate W that you need to apply, so as a function of F. So if we look at the figure 22-18, so depending on the friction, static friction, I believe, I'm sorry, dynamic friction, I believe, you actually will have to apply different force W depending on the distance B. So B is again the distance between the center of rotation to the brake pad contact point with the drum. So this means that as this B grows, as you have a pad width is growing, you will have to you should be able to apply last force W right here to stop the same amount of the torque. So that's what it says right here in the graph. Okay, so with that in mind, homework right here. I'm going to assign this homework in the Blackboard. So that's okay. So next one is the Banda Brake. Banda Brake is again, it is made to make it more efficient, and then apply last force right here by increasing the contact surface between the brake pad and the drum itself. So, basically there are some equations you need to understand. The first one is the Tf, which is the torque you need to handle with the W. So torque has to be equivalent to because there are two forces right here by the string. You need to subtract P2 from P1 times R. So basically we assume that the torque has to be equal to the difference of these two forces times the radius R. Okay, maybe this is not exactly the physical the solution for torque, but it is estimation of the torque, and which is proportional. The Tf is proportional to P1 and P2. And then P2 right here is going to be a function of P1, because if you apply the W, most likely this is the contact point starting first and then going around, and then P2 is going to be the last point that's get into contact with the drum. So P2 is the function of P1 divided by the E to the F times theta. F is a functional friction coefficient. Theta is the angle of the coverage by the brake pad. So meaning that if W is getting smaller and smaller, this will be smaller, and then P2 will be larger. Now, P1 right here, P1 is going to be the function of the pressure pressure acting on this brake pad times the R, the radius times the width. So that means the actual, this is basically the area of the brake area times the pressure is going to be your P1. And then if we discuss about a little bit of the physics behind it, you can actually calculate W as a function of the torque T. So let's see how we could find the W here, just by the same procedure that we applied for the drum pad. Here we have the moment equation set for the point A, rotational point center of A. So assuming the clockwise positive, WL should be positive right here, and then it should be equal to P2 times A. Again, P1 is going to be cancelled because it is acting at the center of A. So this will give us the force W as a function of P2. So you need to be able to evaluate P1 first from the P max, and then once you know P1, you can calculate P2. That goes into this equation to give you the actual value of W. And then WR is the some terms that is about the average wear ratio. Average wear ratio is going to be the function of power over area, and then we'll discuss about this in more detail a little bit later. So with this equation, which seems to be kind of a simple structure, and then the only thing that we didn't discuss is this equation that's coming from reference number 4 in your textbook. So if you want to figure out why, just go for this. And the one exercise in your textbook is 22-10, which asks us about calculating TF, and then the TF for a given 120. But I'm sorry, TF is given, and then the this basically is the design problem of a band brake, meaning what you have to do is to calculate T actual, and then compare it with the TF design, and make sure that TF actual is no more than 10% of the TFD. So when it comes to the band brake design, usually we need to focus on the torque to make sure that the actual torque is not going to exceed more than 10% of the design torque T given in the problem. And then the RPM is given also. So assuming it is a woven friction material with the Pmax that it can handle is about 25 psi, and the friction F is 0.25. That's given property of the material. So when it comes to design, again, we need to have some geometry. We need to know some geometry. So without having anything here, no basic data right there. So we will assume that R of 6.0. This is some number that the textbook proposed. Theta roughly 225 degree. W at W is about, I think it's 2 inch right here. Okay, so once all this this is a triangle geometry, so you need to actually apply some figure out some numbers for the R, which is the radius of the band drum, and then theta, the coverage of the brake pad, and then the W, width of the this is width of the brake pad. So once you have this found, some what called prepared, the first thing again is that you try to find P1, because we have the P max pressure given. Once we have the radius and then the width of the brake pad is known or proposed, you can calculate the P1 with this equation. So once you have P1, again, from this equation, you can find out P2. Here you have a 300 P1 over E to the F, which is the friction 0.25 times the theta 3.93 for a given, not a given, but the proposed 225 degree. Okay, so that gives us the value of 112 times 3 pound. So with this number, you can calculate the TF from this equation, estimated equation of P1 minus P2 times R, radius. So this will give us 1126 pound-inch. But the problem is, if you compare this result with the torque friction, design friction, design torque, it's going to be much more than the 720. So if you think about it, you probably have to somehow increase the friction. So that means that we actually change the R, the radius of the drum, to 5 inch. So if it's to 5 inch, then R is going to be smaller, which means that P1 is going to be smaller. P1 is smaller than P2 is also smaller. So that means basically, because P1 is smaller, TF is supposed to be smaller as well. So by reducing the radius of the band brake drum, you will have different number of P1 and P2 values. And then if you substitute these numbers into that this equation right here, you will have the torque value of 782, which is smaller than 10% of the plus 10% of 720. So that should be okay. Again, if you are not satisfied, you can probably do this over and over until you figure out, until you find the TF. Okay, so with this, for lever design, then we need to have some numbers like A and then L in this picture right here. But because we have no basic data, we usually start with the kind of similar number of A to R. So we start with the 5 inch as A, and then L usually is about 3 times of A. So usually if it is 5, then L should be 15 by this design criteria. So with this, W you can actually calculate from this equation. P2 is going to be A over L, so that the P2, which is 93.59 times A divided by L, is going to be W. So once you have this W, this is basically the force you need to apply. And then WR is something you need to also consider, which is the average wear ratio. Again, it is a power divided by area, so that the area is going to be simply just circumference 2 pi r times width. So circumference times width, that gives you the area. Gives us the value of 39.27 inch square. That's your area. And then the PF, the torque, the power is coming from the torque. If you remember for the RPM equation, you can find out the power from this equation, TF, or TF is going to be PF times 63,000 divided by N. That's the TF that we discussed a long time ago for the shaft design. So PF is going to be TF, that's given right here is the solution, times the RPM is coming from original problem right here, and then 63,000, that gives us 1.49 horsepower. So once you have this horsepower, you actually calculate average wear ratio by dividing P by A. That gives us the 0.0379 horsepower per inch square. So once you have this number, you need to check this result with the page the table in page 708, 704, 704. That's, again, this is my 5th edition, 704. Yeah, this is not table, but there are some sections where you can refer to for the weather ratings here, giving us a number, kind of reference numbers like 0.04 for frequent applications, conservative rating, 0.1 for average service, 0.4 for infrequent use. So if it is a frequent, then it should be roughly around 0.04. So I think if you compare this number, it's pretty close to the 0.04, so that should be okay. If it is not, you need to actually do it again by changing the geometry. So here's some homework right here, but I'm gonna again specify all this in the blackboard. Okay, so with this, let's discuss just a little bit about the final exam. So for the final exam, I want to specify the date. I didn't check it yet, but I'll let you know. And then the first thing is that I believe that one of the most important things